So here we can assume that mobile station is starting from x1. So obviously at x1, the signal strength due to base station J is minimal. It is zero, almost zero. So obviously at that point there is no point of choosing in between base station I and base station J. So mobile station would definitely use the signal strength of base station I. So obviously base station I is going to manage the mobile station. As it would progress towards the base station J. So obviously near to X3, you would notice that base station, mobile station would start receiving certain signal strength due to base station J as well. So that is called P minimum, the signal strength, the minimum signal strength, which is noticeable and which can be later on converted into the data signals effectively. So at least that minimum threshold signal strength is P minimum. But obviously at that point, though, the signal strength it is receiving from the J station is also uh, comparable to the base station I. If you would compare, the signal strength because of the base station I is far superior in comparison to the base station J. So obviously at this point also it's not going to hand over or hands off from base station I to base station J. So as it is progressing, so there comes a point X5. At this point, almost the signal strength is same. So obviously this could be one option when the mobile station can work for the hands off, would starts communicating with the base station J. But here also in reality, in practical circumstances, this is also not the good point, because it may be possible that there's a mobile station which is communicating with any base station, and at a particular time um, it is going towards another base station, and in a moment it comes back. So back and forth it is going on and off. So these are considered to be the boundary situations. So at the boundary, sometime it is going out or sometime it is going coming in. So at that time, if we will use the boundary option, this option X5 as an option for handing over the resources to the previous one and lingering on to the resources of the new base station, then obviously that is called the ping pong situation. You keep on hopping from one base station to another base station instead of communicating. You are oftentimes doing handing over or hands off procedure. So many of the resource would go only in handing over the resources and taking over the resources from the new one, and which will adds on to the delay. So this is not the effective option X5. Generally in practical situation, there comes there they choose one threshold. So at the X at this option, you notice that the signal strength of J is around um, somewhat more, and there is a threshold. So during hands of writing code, so uh, the transceiver of the mobile station is looking for that E. So if the signal strength of J is more than E in comparison to the signal strength I, which it is still communicating with, at that point it will start handing over the resources to the previous base station and would start communicating, negotiating with another base station. So in this way, we can somehow deal with the problem of ping pong. That means going back and forth from one base station to another base station. So this is one example. In detail also, there are different types of hands-off, soft handoff, hard handoffs. So and what goes into the design, the software design of those hands-off. We will deal with all those things. The next one is, so if any one of you who is interested more into the mathematical concept, or the simulation of these things, so you can refer to this book. I will share the link of this book with you if you are interested. Otherwise, these whatever I have discussed so far is more than enough regarding the cellular concept, because this is the basics. I'm clarifying, I'm clearing with you. Later on, when we will pick up the individual technologies, I will share the resources with you where from I will teach. The next is, what is the capacity? So you have to know the capacity of the cell. What is the capacity? Because obviously, if we are not aware about the capacity, then how we will increase or decrease our subscriber base? If the subscriber base is increasing within a cell, we should know somewhat a mathematical calculation should be there, some mathematical modeling should be there to understand the capacity of the cell. So to understand in a very layman, so this is very basic modeling, detailed modeling as well based on the probability and all, but this is very basic, trivial modeling. So here in this modeling, suppose on two parameters we are understanding the offered load, and these two typically characterized by the two important parameters. First is the average number of mobile stations requesting the services. So in other way, what is the average call arrival rate at the base station? So how many times mobile users are requesting for the resource? That means how many times they want to call other users. So that is arrival rate is lambda. And once they start their communication, what is the average holding time of the resource? So what is their average length of the time mobile station requiring the services from the base station? That is the holding time t. So if you have to just calculate, that means lambda is the arrival rate, that many users, that is the on an average arrival rate, and on an average holding rate is t. So if you have to just calculate the offered load within a cell, just multiply it, a is equal to lambda t. And with example, if you will see that, for example, in a cell with 100 mobile stations, on an average, out of 130 are generating a request within an hour with an average holding time of 360. So if anyone starts their call, so for 360 durations they are on, they are utilizing the resource, then what would be the average, then the average request rate would be out of 30. So within 300, I mean, so within 1 hour, 30 requests are there. So what is the arrival rate? Lambda 30 divided by 3600, 30 requests 3600. And if you have to calculate the offer load, 30 divided by 3600 into 360 second. What is Erlang? Erlang is nothing but a service channel that is kept busy for an hour, is quantitatively defined as 1 Erlang. So in R, if you will calculate this thing in terms of 1 hour, so then it is Erlang. So that is all based on, then the further calculation is based on the queuing concept. I'm not going into that much detail. This much is enough for you to understand that these are the important broader parameters on which the offered load is going to be determined. Then the frequency reuse. This concept is important because that allows the reusing of the frequency, and because of which cellular concept is in place. So obviously frequencies are limited, and this concept, while discussing about space division multiplexing, when I discuss about the space division multiplexing, I discuss about the frequency reuse. So what is space division multiplexing? We will use the same frequency in different space where there would be no co-channel interference or any channel interference if both cells are using the same frequency. So we are using a kind of a frequency division multiplexing, the same frequencies we are going to use, but we will implement it using space division multiplexing. And in practical, cellularization uh, is a concept that realize the space division multiplexing, because here you come up with the different cell, and those different cell being allocated different frequency in such a way so that there would be minimum interference. So here, as you can see in this example, so we have divided, so we are using here the hexagonal model, and we have divided our complete range of operation into different cells. Now, after dividing your complete sector or the region into cells, the next important parameter is that how will you allocate the frequency. So frequency allocation is important, and how we generally allocate the frequency is depend on minimum interference criteria. So here we have allocated, so if you will notice this cluster, so here we are using a cluster of 7 frequencies. We can use a cluster of 3 frequencies. Even the choice of the cluster is very important, that how many frequencies you are using. If you will use obviously more number of frequencies, the channel interference, the cell interference would be less. So here we are using the 7 frequency. The 7 frequencies are there in one cluster. F1 being allocated here, F2, F3, F4, F5, F6, F6. These all are manually. So here, when initially the service provider start operating, then first and the foremost thing is sectorization. First you sector it out, you cluster it, then you make cells, and then the frequency allocation to all these cells are very important. So here the 7 clusters are using, so 7 cells are making one cluster. So here in this dark shade you can see this is one cluster. So one cluster comprises of all the frequencies which been allocated to you and which you want to reuse. So here what concept you have come up with? You have come up with a cellular concept in which you have divided your clusters into 7 different cells. Those different cells you have been allocated with different frequencies. Now this F1, F2, F3, F5, F6, F7 being allocated to one cluster. So in one space we have used it. Now the same frequency we want to use in some other space so that interference would be less. So what are we doing? We will go to the next cluster and we will allocate F1 to this one. So here you can see this reuse distance. So from one cluster to another cluster, if you will calculate the distance, this is called the reuse distance. If the reuse distance would be more, obviously the interference would be less. So there are calculations how you can calculate this reuse distance. So here there's a relationship D is equal to, you can come up with this relationship if you have any interest. But just for your broader understanding, in abstract way, you can understand that if more the distance, so the better it would be if the reuse distance is more. 3 cluster operation you can do if you've been allocated to a smaller range of frequencies. You can come up with a 3 cluster formation of the cell. Here it is 7 cluster formation. Now we will understand 2 more important factors: cell splitting and cell sectoring. So before cell splitting, just let me mention about the cell sectoring. Generally, uh, we in ideal situation we see as uh, our base station is using omnidirectional antenna. But suppose if you have to sector out, means if you have to again reduce the co-channel interference, because if you will use one frequency and using an omnidirectional antenna, that frequency will go in all direction, and that may leads to an interference so with the next cell if you would have allocated the same frequency. So suppose if you want to reduce uh, the reuse distance, because that's only there on the table, the number of frequencies are very limited, and those frequencies you somehow want to accommodate, so this cell sectoring gives you a way of somehow reducing the co-channel interference. What you can do, so here in omnidirectional antenna you can see that there is only one frequency. Obviously if you would use that frequency, it would go in all directions, so the interference would be less because of the less reuse distance. Whereas if suppose within a same cell we sector it out, and here we are using 120-degree sectoring, and you can use 90-degree sectoring, 60-degree sectoring based on your frequency requirement. What is your frequency allocation and what is your requirement? You can plan it accordingly. So here for an example, if we are using three frequencies C, A and B, so obviously in A sector we will use the directional antenna, the 120-degree directional antenna, so so that even when you are using it here, so within the next cell you can plan your frequencies accordingly. So within the next cell you can reuse the same frequency, whereas in case of the normal situation we have seen in 7 sector formation here, in 7 sector, when we have used this f1 after our reuse distance of the f1 in the next cluster. But within a cluster, if you have to reuse the same frequency, if the frequency allocation is very constrained, if you've been allocated very limited frequencies, so within one cluster, if you would have to use the same frequencies, you can use the concept of sectoring. Within one cell, you can sector it out, you can reuse the frequency then in the next because now you're not no longer using the omnidirectional antenna, the impact of your channel would be very minimum to the next cell within the same cluster. So that is called the sectoring. Now splitting is somewhat different. What is splitting? How you will split the cell? So splitting cell is based on the offered load. So suppose if this is the formation of your cluster, and here these all cells which are not resplitted, which are not splitted, these all cells are those larger cells where the density is very low. That means the mobile users are very less. So in these cells the mobile users are very less, so obviously the limited resource, only one base station would be sufficient to operate or to somehow manage the cells, like in rural areas. So in rural areas the density is very less, the mobile users are less, so obviously one base station would be enough to somehow manage those mobile users. Whereas if you would notice any city, any city area, any downtown area, so in that situation, within one cell, if you would notice, there is a pocket of region where the concentration is more, where the density of user is more. So if the density of the user within that region is more, so obviously they demand more number of channels, more resources, so you can further resplit. So here how they have resplit, so just imagine this one, this cell, they have re-splitted it, so a smaller cell with higher density. So here once again re-splitting means once again you come up with one more base station there within a one cell. So within one cell, once again you are re-splitting, you are resectoring the zone, which generally based on the user requirement they keep on checking. So service providers keeps on verifying that where the concentration is more. If somewhere they see that the user base is more there, if new subscribers are catching up in numbers there, so obviously the next task would be to resplit that zone, to resplit that cell, and within that resplitted cell give more resources. That means install one more base station. So that is called cell splitting. And cell sectoring we have discussed. So this is about the frequency reuse. So uh, here in this example, you can see 7 frequency reuse we have seen. So here the left side is 3 frequencies, F1, F2, and F3. And here in comparison to the right side, if you would notice, the frequency reuse distance is less in 3.1. Now there comes one dilemma when you will start providing services. So whether your cell size should be less or should be more, because with respect to your cell size, the infrastructure cost is dependent on your cell infrastructure, the cell size. If the cell size would be more, so obviously less number of cell would cover up the whole region. Then the infrastructure cost would be less. But the problem with that sort of an infrastructure is it would end up supporting less number of subscribers. Whereas in contrast, if you would notice, if you will reduce the cell size, obviously within that region which you are serving, the number of cells would be less. Consequently, the infrastructure cost would increase. So there are certain advantages and disadvantages we will notice that if you will reduce the cell structure. So we will first look into the advantages with respect to the smaller cells. The advantage is the higher capacity. Obviously, if the cell size would be less, the infrastructure cost would increase, and you are increasing the infrastructure cost, as we have understood in case of cell splitting. In cell splitting, we are reducing, we are further splitting the cells, we are increasing our infrastructure, we are in we are increasing our infrastructure so as to reuse our frequencies more, so that we can accommodate more number of clients, more number of subscribers. So obviously it would amount to increase the capacity of our system. And this is also very critical. The transmission power would be less, because obviously when the cell size would be small, if the cell size is small, then then the base station which would operate has to operate on smaller power. So the power utilization would be less. And the local interference, because if the cell structure is small, the interference would be local only because your transmission power is less, and your transmission power is less, so your signal would not end up mixing up with other cell signals, because by the time your signal, which is of less power, would reach the next cell, it would be just a noise. It would simply decay. So the interference would only be local. And this kind of infrastructure where your cell structure is less would increase the robustness of the system, because if a small cell would not be able to function properly because of any reason, the impact would be highly local. Whereas in comparison, if the cell structure is more, the impact would last long. The impact would be for large user base. Whereas in case of the smaller cell size, the impact would be highly local. So it leads to the localization of mm, any problem. Obviously, as I have discussed, there are certain disadvantages as well, because if the cell size would be less, it would require more infrastructure to come up with, increases the cost. And obviously if the cell would be more, so the end user would end up hopping from one base station to another base station would be more, and it leads to more number of hands off. And when you are handing over, it is an additional requirement, though it is very critical, but it is an additional requirement, so it's a sort of a burden on the system. It may increase the delay in communication, and several times you may even lose the connection while hopping from one base station to another base station. So it is critical, and it increases if the number of base stations would be large because of its size. And meticulously you have to plan your resources while allocating the frequencies. You have to meticulously plan so as to reduce the co-channel and co-cell interference. If you have a very limited frequencies, then it is very difficult for you to plan your frequencies uh, for smaller cell structure. Most of these things we have discussed. One more thing is remaining, that what we have discussed so far is first we have divided our region into different spaces, that is called cell, and each cell being allocated its frequency resources using FDM, frequency division multiplexing. So we have allocated that thing. So initially we have divided the space, so that is called space division multiplexing. And as I have mentioned, that one technique you're not going to use solely, entirely exclusively, one technique is not going to multiplexing, one technique is not going to function. So here we have used two concepts. One is initially we have divided the space, so that is space division multiplexing, and then we have allocated there we have allocated those different spaces with different frequencies. Now if you will allocate it statically, that is called the fixed channel allocation, wherein that may be one way of dealing with the situation. But suppose if in the nearby cells, so within all the cells, uh, the load is not constant, it's keep on varying from one base to another base. So in that situation, suppose if two nearby cells are there, one cell been allocated certain frequency, another cell been allocated one frequency, but in one cell the number of subscribers are more at a particular time because of mobility. People are moving, mobile users are moving from one base station to another base station. So at a particular time, suppose uh, in one base station, with respect to one base station, the number of users and demanding resources would be more, and that base station doesn't have that much resource to entertain the request. In that situation, if it is not fixed, but whereas it is a dynamic channel location, it can take over certain resources from the nearby base station and utilize it effectively so as to entertain their request, the current offered request. So that is called the borrowing channel allocation or the dynamic channel allocation. This is also one way of dealing with uh, the variable offered load. That's all in this lecture.